We rarely notice the blocky, glowing numbers that quietly track our daily routines, starting from the moment the alarm triggers at dawn. But this exact numerical design is a universal standard, providing the primary readout for everything from kitchen appliances to the first generation of portable calculators. Despite how effortlessly we read these digits as whole numbers, they are actually composite shapes, built from a specific arrangement of independent linear lamps. Because these numbers are fragmented pieces acting in perfect coordination, every change in the readout requires a precise, invisible choreography to decide which parts stay dark and which ones glow. If we deconstruct that figure 8, we find it is composed of exactly 7 independent light-emitting diode segments. To manage this hardware, the computer's processor operates entirely on binary signals, ones and zeros, while we require base 10 digits. To display a 0, the machine coordinates 6 separate signals to activate segments A through F, intentionally keeping the center segment G dark. If the main processor had to manually toggle each of these 7 switches every time a digit changed, the complexity of the wiring and the code would increase with every new number added to the display. To solve this, engineers use a dedicated microchip known as a decoder integrated circuit, such as the 7447 model. This chip sits between the processor and the physical display, acting as a high-speed translator for the incoming data. It receives a compressed 4-bit machine code called binary coded decimal, or BCD. The decoder takes this 4-bit machine input and automatically expands it into the 7 physical signals needed to light the display, removing the burden from the main processor. Inside the decoder, the routing of electricity is governed by a truth table, a hardwired set of logic rules built into the chip's circuitry. This logic flow shows the rule for a 0. When the 4-bit code for 0 enters the chip, internal gates route current to outputs A through F, blocking it from G. As those signals reach the display, the outer ring illuminates to form the 0. When the binary input switches to the code for the number 1, the internal logic gates instantly redirect the current, sending it only to lines B and C. On the display, the segments instantly update, leaving only the 2 right-side vertical bars lit. This isn't software making a choice. It is the physical architecture of the microchip automatically routing electricity based on how its internal transistors are connected. Mapping the data is only the first step. For the LEDs to actually glow, the electricity must complete a physical circuit. In a common cathode setup, all 7 LEDs share a single grounding wire. To turn a segment on, the decoder provides the positive voltage needed to complete that specific path. Conversely, a common anode setup shares the positive power source, and the decoder completes the circuit by providing the ground for the specific segments it wants to light. Whether it provides the power or the ground, the decoder ensures the correct circuit is completed at the exact microsecond the data arrives. As devices needed to display words rather than just numbers, engineers scaled this same decoding logic to more complex grids. The 16-segment alphanumeric display added diagonal lines and split the horizontal bars, using more LEDs to form a full alphabet. Though the number of LEDs increased and the binary input grew longer, the decoder's role as a hardwired translator remained the same. This method of decoding data into physical light is what allowed early electronics to expand their displays without requiring a dedicated wire for every single pixel. Today, that foundational principle operates on the scale of massive city block billboards. These million-pixel video walls rely on a hierarchy of shift registers, multiplexers, and receiving cards, all acting as direct descendants of the logic found in the 7-segment decoder. So, the next time you look at a digital clock, remember the high-speed translation happening on your nightstand. The 7-segment decoder is the ancestor of every modern screen, the bridge that first allowed machines to show us what they were thinking.